Good evening, Professor.
I can always count on you.
I just got on my computer to do some homework and I was like, oh my goodness. Let me
Yep,
see what.
we're doing an extra one. And we'll probably do more and more extra ones as we get closer and closer to finals.
Oh, yeah.
Hey, listen, I am so sorry I have not had a chance to type up solutions yet to measure two material. I've been really busy with grading and, teaching and advising, but that is the next thing on my list is to create those solutions. We can go over any of those. Hi, Malila. Malila is the student who requested this pop-up office hour. Malila, can you hear me okay? You got to unmute. You're on mute. Hey,
Yes, I can hear you.
hey, great. So Malila, meet Nura. Nura is one of our regulars from the Tuesday, Thursday class. Malila's in the Monday, Wednesday class. And Malila asked for this extra office hour. So I'm going to ask Malila first for her questions, if that's okay with you, Nura.
Absolutely.
Okay, Malila, I'm going to pin this and you're going to ask some questions.
Okay. I don't really understand like the first question of the quiz, the one I was supposed to be due today. I don't understand it. Like
Okay.
when you give like a set and it's like multiple sets within one set,
Oh,
like it's in the
you mean
last
take
week's
home quiz
notes.
9? Are you talking about take home quiz 9 that's due on Wednesday or Thursday?
No, the one that was due today.
Oh, the one that was due today. Oh, okay, the set one. Okay. Um, well, no, the one that was due today was quiz 8.
Wait.
Are you looking? The one that was due to 8 was today was two induction problems. Problems 2 and 3 were induction problems, and problem 1 was a summation problem.
Oh, okay. Um,
Maybe you're looking at the wrong, you're looking at the
I
quiz, not, you're looking
I
at
think
quiz 9.
I definitely did look at quiz 9.
But you had
No, I did
told
not.
what?
I looked at something else.
Did I upload the wrong quiz 9?
Wait, no, no,
No,
no. I
quiz
think
9 is sets. Quiz 9 is sets. Quiz 8 is induction and the summation formula. Did I do something wrong? Did I screw that up?
no, no, you did not. I looked at something else.
Measure 2 material. Maybe you were looking at measure 2
I
material.
was looking at measure two.
Sure. In chapter 6.
Yeah, I looked at special homework.
Hey, yeah, the special homework number 6.1. Shall we look at some of that?
Yes, please. I still don't understand it.
Oh, I know. These are really challenging. I tell you what, I'm just going to let you know that in the special homework for section 6.1, problem number 1, you should look at the office hours from last night, okay?
Mm-hmm.
From last night, which was 04 27 25, because we worked through problem number 1 pretty thoroughly,
Okay.
but we can look at number 2 or number 3. You want to look at number 2 or 3 together?
Sure.
Sure.
Yeah.
Okay.
Yeah.
All right. So these all depend upon interval notation. So in number 2, there's a set called B sub I. Called an indexed set. And the definition of B sub I is that it's square bracket I, comma, to I plus 1 square bracket. And we're supposed to find each set. Okay? So Oh, the first thing we're going to do is find the union from I equals 0 to 3 of the B sub I. Okay? And then we're going to look at the intersection and we're going to look at an infinite union and an infinite intersection. Okay?
Mm-hmm.
All right. So, do you have a question before we kind of dig in?
No.
All right. The easiest way to understand any of the union or the intersection, whether it's from I equals 0 to 3 or I equals 0 to infinity, is to first really understand what these sets are talking about. So let's dig in. Let's understand the set B sub I. Okay? Because if we don't understand what the set B sub I means, then we don't have much hope of understanding unions or intersections involving that. Does that make sense?
Mm-hmm.
All right. So you and Nura can help me, but we're going to start with I equals 0. Okay. So for I equals 0, let's see what we're really talking about. So we go to this definition for B sub I, and we're going to plug in I equals 0. All right. So we're really looking to understand first the set B sub 0. So I is 0. That means everywhere you see an I, you plug in 0. Does that make sense?
Okay.
I mean, that's just the way the notation works. It's what it means. Uh, it means this is an interval of the real line, and it starts at I and includes I. That's what the square bracket means. It means, hey, it's like a closed hole. We're going to include the left endpoint, and the interval ends at I plus 1 for whatever I is. So when I is equal to 0, what do we put for the left boundary there? We just plug in I equals 0. Do you see what I mean? So that interval starts at 0. Does that make sense? I'm just inserting.
Okay.
Yeah,
Mm-hmm.
all we're doing is substitution. Wherever you see an I, which is here, here, and here, we're going to just plug in the value 0 and see what happens, okay?
Okay.
All right, so when we put an I in 0 in for I there, this interval starts at the number 0 and it goes up to 0 plus 1 because that's just what the definition says, okay? Square bracket. So if we just simplify that a tiny bit, it's what we call the unit interval from 0 to 1, inclusive. It's the closed unit interval. The square brackets, they mean something. It means include the endpoints. Include the endpoints. And the endpoints of this interval are 0 and 1. So if we drew a picture, and a picture really helps, B sub 0, here's the real number line. It starts at 0 and it goes to 1. Here's 2 and so on and so forth. But it just is all the real numbers between 0 and 1, including 0 and including 1. Does that make sense?
Mm-hmm.
So now let's take a look at the next B sub I when I is equal to 1. So let's look at B sub 1. This is B sub 0. It's these numbers between 0 and 1. All right, so you help me with B sub 1. I is 1, okay? So everywhere we see I, we're going to just plug in 1, okay?
Okay.
So what should be the left endpoint of B sub
1.
1? Good, 1. And what should be the right endpoint?
1 plus 1.
It will be. Good. And so if we simplify that just a little bit, It's the closed interval that starts at 1 and includes 1 and goes to 2. Does that make sense?
Mm-hmm.
All right, so let's draw b sub 1. Well, it starts at 1 and it includes 1, so we'll put a little square bracket going this direction. And it goes to 2 and it includes the 2. And it's also every real number in between. There's an infinite number of those real numbers. It's not just integers 1 and 2. It's all the real numbers that are in between, like, well, pi over 2 is in here somewhere. 1.5 is in here somewhere. 1 9/10 is in here somewhere. There are an infinite number of real numbers that live between 1 and 2 inclusive, including the 1 and the 2. Does that help?
Mm-hmm.
So now let's take a look at what b sub I is when I is 2. In other words, let's find b sub 2. What is b sub 2 going to be? Where's it going to start?
2.
And where does it end?
2 plus 1.
Uh-huh. So what is that really? It's the interval from,
1 to 3. Oh, 2 to 3.
okay, great. And if we drew that, we could, you know, we could say, okay, well, let's keep going. We're gonna draw another one. Here's 3, and it's everything between 2, including the 2, and 3, and in between, everything in between too. See what I mean?
Mm-hmm.
And then finally, when I is 3, because that's as high as we're going to go for these, what is b sub 3 going to be? Where is it going to start?
3.
Uh-huh. And where does it end?
3 plus 1.
Uh-huh. So it's really the closed interval. I say closed because we're including the endpoints. We call that closed from 3 to 4, right? So we could draw one more. I think we can fit one more in there. Let's keep on going. And here's 4. So everything between 3 and 4, including the 3 and 4, is in the set that we might call B sub 4. Does that make sense?
Mm-hmm.
And in fact, it might be less confusing if I put these numbers up here. Okay. All right, great. So, here's B0, here's B1, here's B2, here's ooh, did I call it B4? What should I have called it?
B3.
Thank you. Good. So you get it. All right. So now let's take a look at the union. The union, when I starts at 0 and goes up to 3 of the B sub I, what that really means is, okay, I starts at 0, so the first set is B sub 0. Union, see, this is kind of like sums and products, but it's a union. And what would be the next set? The I increments by +1 as we go through it. So from 0, we
B1.
go, yep, good, union.
B2.
And then what do I write?
Union.
Good,
B3.
exactly. So what we're really doing is we're going to take the union of B0, which starts at 0 and ends at 1, and includes the 0 and the 1, union the interval from 1 to 2, union the interval from 2 to 3, union what?
The interval from 3 to 4.
Exactly. In other words, we want to express the interval of the real line that includes x if x is in B0 or x is in B1 or x is in B2 or x is in B3. Do you know how to write the union of these sets using interval notation?
No.
Where does it start?
A 0.
Yeah, it starts with the x right here. And then it's any x in here or in here or in here or in here. Where does it stop?
4.
Right. So it's the closed interval from 0 to 4. In other words, if we were going to draw the picture of the union set, here's 0, 1, 2, 3, 4. We're looking at any real number x that is between 0 and 4 inclusive. Does that make sense?
Mm-hmm.
Okay, so that's how we would evaluate the union. You just ask, how could we write the set that has x's that come from here or here or here or here? Oh, it's any x that is in the interval from 0 to 4 inclusive, because we're including 0 and including 4. We're including the endpoints because those are square brackets. All right, now let's look at the intersection. And having the picture there should help us. If we want to look at the intersection from I equals 0 to 3 of the B sub I, we're asking, well, it's these sets, but with an intersection symbol in between them. So it's x's that are in this set and intersection, the set from 1 to 2, intersect the closed set from 2 to 3, intersected with the closed set from 3 to 4. So intersection is our AND operator in setland. We're asking what elements are in here and in here and in here and in here. Hey, Stanley, are there any elements X that are in all 4 of those?
No.
That's right. There is no x that's in even 2 of these except the integers, but the integer 1, for example, it is in B0 and in B1, but the integer 1 isn't in B2 or B3. So there is no real number that is in all 4 of these. So the intersection of all of those is actually the empty set.
Okay.
Now, if we just kind of understand, hey, B0 goes from 0 to 1, B1 goes from 1 to 2, B2 goes from 2 to 3, etc., because there's our definition of B sub I right there at the top. And we ask ourselves, what if we took the infinite union of B0, union B1, union B2, union B3, union B4, union B5, keep on going, keep on unioning forever and ever? That's what it means to ask about the union from I equals 0 to infinity of the B sub I. We're asking to play this game of taking the union forever after. It's an unbounded indexing situation. We just keep on going. And if we understand the picture of what the general B sub I looks like, if we understand this is B0, this is B1, this is B2, and it would just keep on going, and we try to take the union of all those, what do you think we would get? Well, we're just going to try to figure out a way to write this idea as a single interval. What would be the left boundary? What would be at the left if we said this set union, this set union, this set union, this set union, keep on going, what would be at the left?
0.
That's right. 0 is on the left. Now let's think about what would be on the right. We're not stopping at 4 because we're going to say B0, union B1, union B2, union B3, union B4, union B5, keep on
Infinity.
going. Yes, exactly. And since infinity is not a particular number, but a concept, we never use square brackets with infinity. We always use soft brackets because it's not really possible to include the number infinity as an endpoint. The point with infinity is there is no endpoint. It just keeps on going forever and ever and ever to the right. You just keep on going. So that's exactly right. Now the intersection from I to infinity is going to be a stricter kind of situation than even the intersection from I equals 0 to 3. Here we're asking, for even more. We're saying, oh, we're going to intersect 0, 1 with 1, 2, with 2, 3, with 3, 4, with 4, 5, with 6, 5, 6. We're just, and so the question is, what elements in the real number line would be in all of these? Is there any real number that is in all of these?
No.
That's right. I mean, there wasn't even any real number that was in 4 of these intersected together. There's certainly no real number that's in 4 of these intersected with an infinite number more of those sets. So that is infinity as well. Did that help?
Mm-hmm. Okay.
And then the last question is, are the sets in the collection mutually disjoint? Now that's a different question. Are the sets in the collection B0, B1, B2, dot, 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 mutually disjoint? And here, the definition of the set and our pictures and mutual disjointness should help us. So here's our definition of the set. Here's our picture. It is square brackets. So when we looked at B0 intersected with B1, intersected with B2, intersected with B3, mutual disjointness would require that if we took any 2 of these sets, not all of them, but any 2 of them, and looked at the intersection, that intersection would have to be empty. So let's rephrase the question. In other words, if we take any 2 of the sets, BI and BJ, where I and J are different. So we're taking 2 different sets. The question really is this: is BI intersect B sub J equal to empty always? In other words, is it true that if we take any 2 of these sets, no matter which 2, that their intersection is always empty? What do you think?
Mm,
We're only taking two at a time. So we could be taking these two. Is the intersection of these two empty?
yeah.
Is it? Careful.
We could do BO and B3.
It's true that BO intersect B3 is empty, but that's not what mutual disjointness says. You don't get to pick the two. I can see how you might say think that. We don't get to just pick two and say, hey, I have found two and their intersection is empty, so these are all mutually disjoint. That's not what the definition says. It says if we take any two of the sets, their intersection has to be empty. In other words, if we take these two, their intersection has to be empty. If we take these two, their intersection has to be empty. If we take these two, their intersection has to be empty. If we take these two, their intersection has to be empty. Or the intersection of these two, that has to be empty. The intersection of these two has to be empty. Do you see what I mean? We have to check pairwise. If we take any two at the same time and look at their intersection, that intersection has to turn out to be the empty set. Well, is that actually the case?
No.
No. Can you give me two of these that has an intersection that's not empty?
You said I can't pick. Um,
You can't pick if you're trying to prove in the affirmative. You'd have to look at every pair and look at their intersection. But if the answer is no, they're not mutually disjoint, all we do is find a pair that exists such that their intersection is not empty. The negation of a big and statement is the disjunction of the negations. So if it's not true that taking any two and intersecting them yields an empty set, if that's not true, then it means we can find two and take their intersection, and that intersection will not be empty. And in fact, that's what we can do. Can you give me two of these sets that have a non-empty intersection and tell me what is in their intersection?
I don't understand.
All right. The answer is no. These are not mutually disjoint sets because we can find BI and BJ with I not equal to J. So two different sets, but such that their intersection is not the empty set. In other words, just think about it. Let's take B sub 0 intersect B sub 1, okay? Right? So I is 0, J is 1. I and J are different. So we're looking at two different sets. But when we take their intersection, we're looking at the intersection of the set from 0 to 1 and the set from 1 to 2. Okay? Do you agree that that's B0 and this is B1?
Mhm.
When we intersect these sets, they do have some real numbers in common, or they have a real number in common. What is in both of these? What real numbers are in both of these? The square bracket means we're including the endpoint. Well, 1 is in B0. It's the rightmost endpoint of B0. 1 is also in B1. It's the leftmost endpoint of B1. So in fact, you could write it two different ways. I'll show you a new way to write it. We could say, hey, the set from 1 to 1 is exactly the intersection because 1 is in here and 1 is in here. But the other way to think about that set is just the singleton set with just the number 1 in it. 1 is in both of these. So the number 1 is in their intersection. So we found two different of these sets, BI and BJ, whose intersection is not empty. This is not the empty set. There's something in there. Namely, they share that endpoint element 1, okay? So the sets in this collection are not mutually disjoint. Because you can find, I mean, this isn't the only, we could say B1 intersect B2. They would share the number 2 in common. B2 intersect B3, share the number 3 in common. It would have to be true that no matter which 2 we took, the intersection is always empty. And that is not the case with these square bracket sets. Okay. But I can show you an example where we do have mutual disjointness. Let's just call this number 2 prime. Let's let Ci be soft bracket from I to I plus 1. Soft bracket. And this is going to be I equals 0, 1, 2, 3, dot, dot, dot. Are the sets in the collection curly C, which is, C0, C1, C2, keep on going. Are those sets mutually disjoint? Well, let's just take a look. What are these sets? C0 is soft bracket 0 to 1. C1 is soft bracket 1 to 2. C2 is soft bracket 2 to 3, and so on and so forth. If we drew these on the real number line to kind of get an idea of what they look like, here's 0, here's 1, here's 2, here's 3. These are soft bracket sets. We're not including the endpoints. So C0 is everything between 0 and 1 exclusive. We're not including the endpoints. We're excluding the endpoints. And C1, well, it doesn't include 1 and it doesn't include 2, but it's everything in between 1 and 2. It's the open set between 1 and 2, and so on. These sets are mutually disjoint because there's no overlap between any of these sets, even the ones that are right next to each other, like C0 and C1, or C1 and C2. They don't share any elements in common because there is no overlap. Neither one of these share the number 2. So the answer to this is yes. Ci intersect Cj is equal to the empty set whenever we pick an I that's not the same as j. Of course, if we took C1 intersected with C1, that would not be empty because C1's got lots of things in it, an infinite number of real numbers. But if we pick two different indexing numbers so that I is not equal to j, their intersection is always the empty set because none of these sets contain the endpoints. Does that make sense?
I don't understand.
You do understand or you don't understand?
I don't.
Oh goodness. All
No,
right.
no, because you said CI. I don't see CJ.
All right. Okay. So C0 intersect C1 is empty. There I is 0 and j is 1. C0 intersects C2 is empty. Their I is 0, J is 2. C0 intersects C3 is empty. Do you agree with these statements that C0 intersects C1 is empty?
Mm-hmm.
Because they don't share an endpoint. Everything in C0 is less than 1. Everything in C1 is greater than 1. There is no X that is both less than 1 and strictly greater than 1. So C0 intersects C1 is empty. You could take I equals 0 and J equals 2. So we're looking at this set and this set. These two sets have no elements in common. Their intersection is empty. It's easier to see that when they're further and further away, like C0 intersects C3 is empty. Now we can't actually check all the different situations where I is not equal to J, but we can check enough of them that we get kind of an understanding. Like another one would be looking at C1 intersects C2. No, let's look at C1 intersects C2. In other words, look at when I is 1 and J is 2. The point is, whenever we pick an I and a J, we're picking them to be different indexing numbers. So we're actually looking at different sets and taking the intersection of two different sets. That's all we mean by whenever I not equal to J. Saying this just means CI is not the same set as CJ, because I and J, when they're different, will yield a different CI and CJ. So, I mean, we can do this until we, feel like we understand that no matter what I we pick, like I equal 1, and what J we pick that's different from I, like J equal 3, that no matter what pair I and J we pick, as long as I and J are different, CI intersect CJ will always wind up to be the empty set. Like we could pick C2 intersect C3. In other words, use I equal to J equals 3. As long as the indexing numbers are different, we're looking at two different sets. C2 and C3 are different sets. Their intersection is empty. See what I mean? So, I mean, we cannot list every single CI intersects CJ. It would be impossible. It would be an infinite list, because there are an infinite number of pairs, I and J, where I and J are different numbers. But this idea that if we take any two of these C sets, as long as we pick two different ones, that's all we mean when we say I is not J. We're saying we're actually picking two different ones of these. If when we pick any two and look at their intersection, if that always turns out to be the empty set, then we can say the collection is a mutually disjoint collection. These two intersected, that's an empty intersection. These two intersected, that's empty. These two intersected is empty. These two intersected is empty. These two intersected is empty. These two, you could just keep on going. But I think that eventually we look at enough examples to understand, oh, as long as we're looking at two different ones of these, they'll have nothing in common, even if the two sets that we're choosing to look at sit adjacent to one another. Because that's really the only time that it might even be close enough that they might have something in common. Does that help?
I think this question is just one of them that I don't really understand.
I understand. That happens. You know what you should do is sleep on it and come back and look at it again
Yeah.
tomorrow or the next day.
Yeah, I'll look at it again, and if I have more questions, I'll ask you on Wednesday.
Okay. Um, so we've got Stanley. We don't usually see you here. Do you have a question?
Hello. Can you hear me?
Yes, we can hear you.
Oh, yes. I was wondering, what is this three? Is it this week or next week?
When is test 3?
Yes.
It is Tuesday for your class. It's
Tomorrow?
no. Oh, it's pushed off a week. Didn't you email me and ask me this question?
Oh, no. Wait, I emailed this the same,
Yeah,
10 minutes ago.
yeah, I haven't announced the test because remember we postponed test 2 by 1 week?
Oh, yes, we did.
We did. So if you check the class notes that are posted for tomorrow, it says the test 3 is next to for you for your class, it's next Tuesday.
Okay.
You're welcome.
Thank you, Maria. And I don't think if you apply for that. You see, on the special homework we have, the
Mm-hmm.
homework we have, the website. You see, for the first question, there's A and B. I don't know how to answer that question. What is
Oh,
it? Just
is special
true
homework for 6-1 or for 5-1?
for 6-1. Yes.
Okay, so what problem?
On the first point, it's easy question, but you say put true. Because I don't really understand. Say for N equal 5 or for all integer or, but I don't really understand it. But
Are
the
you talking
question.
about question number 1 on special homework 6.1?
Oh no, no. You see the Cengage. You see the homework like it was on Cengage, the
Oh, okay.
website.
So, all right,
Yes.
fine. That's fine. So we can certainly look at the homework um, on WebAssign. Hang on.
Thank you, Professor.
You're welcome. Are you leaving?
Yeah.
Okay, uh, Stanley, I'm going to share my screen.
Okay.
All right, so I'm looking at the homework
Okay, this
6-1.
one, the first one.
Yep,
Yes.
yep. Okay, can you see that? Uh,
Oh, that's not it. Okay, yes, this one. I'm doing it right now.
what problem?
Okay, this the first problem. You see, you say let A equal to all your number.
Yeah, we actually answered this question in the office hours last night, but I'll look at it again with you.
Okay, yes.
All right, so it's WebAssign 6.1, and it's problem number 1. And is it can you mute, please?
Oh, yes, sorry.
All right, so I think you're looking at the set A. Is this, I'm assuming that you can answer the first part. What does it mean to say that X is a subset of Y is false? Or did you have trouble with the first part? You're still muted.
No, I can answer the first part because the
Okay,
subset that mean the element that's in X is also in B, right?
yeah. That there's an element in X that's not in Y. That's what it means for it to be false. So A is a set of multiples of 5. In other words, A is a set of integers such that, n such that n equals 5r for some integer r. And in fact, Stanley, we're going to do one of these at the beginning of class tomorrow. But it's kind of interesting to think about them. B is a set of m in Z such that m is equal to 20s for some integer s. And the question is, determine which of the statements are true and which are false. Enter true if the statement is true, but enter a number that can be used as a basis for counterexample if the statement is false. So let's just review. what it means for A to be a subset of B and B to be a subset of A, because let's just review. A is a subset of B means if X is in A, then X is also in B. Okay, that's what the definition of subset means. You know, if an element X is in A, then X is in B. Now, B is a subset of A means, you tell me.
It's if there's an element in B, that's implied there's an element in A.
That's exactly right. So it's an if P then Q kind of definition. Oh, I wanted a red one. I wanted red here. You know, it's an if P then Q. And we know that the negation of if P then Q is P happened and Q failed, right?
Yes.
So if it's not true that A is a subset of B, it means that we have an X that's in A and X is not in B, right?
Yes.
So when they ask us for a counterexample, it means so if A is not a subset of B, in fact, I don't even need an if. A is not a subset of B means that the negation of this is true. In other words, X is an element of A and X is not an element of B. In other words, we get P and not Q. And the same thing for B is not a subset of A. It means that there's an X that's in B, you know, P is true, and X is not an element of A. So when we look at these sets, it's really, really helpful to kind of list some of the elements in the sets to get an idea whether A is really a subset of B, whether B is really a subset of A. Okay, so let's see what elements are in A and B. All right, so A is the set of multiples of 5. Do you agree that that's what this means? It means N is an integer and N looks like 5 times R.
Yes.
So let's, yeah. So by the way, R could be 0. Do you agree? Is 0 an integer?
Yes.
So N equals 5 times 0 could be one of the elements in here. In fact, we can kind of think of 0 as being the middle element, okay? Give me some of the other elements that are in A. So instead of R equals 0, we might use R equals 1 or R equals 2 or R equals minus 1. So what are some other elements in A?
4.
4? Stanley?
Yes, because you say it can be any number, right?
R can be any integer. The elements in A can't be anything. The elements of A have to look like 5 times an integer. So is 5 in A?
Yes.
What else is in A? What about when R is 2? What would N be?
Okay. It is going to be 5 times 2. Okay, now you can make 15. Okay, now I got it. Yeah.
Does that make sense? But R could
Now,
be
yes, now I
negative,
can.
right? R could be negative
Yes.
1
It-
or
Yes,
negative
five,
2.
negative 10.
See, aren't these the multiples of 5 that we're listing here?
Oh, yes. Now I got it.
Okay. And you can see that B is a different set. It's the multiples of 20.
30, 60. Oh,
See it?
now it's six. Yeah, it's a six.
So sometimes we just have to read the definition and just start plugging in integers R and see what happens. All we know is R is an integer. So plug in R equals 0, plug in R equals 1, plug in R equals -1. And then we get a better idea of what A and B really are,
Yeah, that makes much sense now.
right? And we can see now, is A subset of B? In other words, is every element that is in A also an element of B? In other words, if X is in A, does that mean X is in B? Like take 5. 5 is in A. Is 5 in B?
No.
No. But is B a subset of A?
No, because 15 is on.
Wait
Okay,
a
no.
minute. Isn't look at all these
20, 20.
elements of B. Aren't they all
Yes.
multiples of 5?
Yes.
Yes. Right?
So the element have to be on the first one, not both of them.
That's right. For the subset inclusion to fail, you have to find an element that's in A but not in B.
Oh, okay.
So like 5, 10, 15, but you couldn't use 20 because 20 is in B. So you have to use one
Yes.
of the ones that's in A but not in B. All
Okay,
right.
no.
All right. Yeah. And again, we discussed this again last night as well if you need more explanation, but I think we've really gone through it now again. Poor Nora.
Thank you very much.
You're very
If
welcome.
I Yes, if I need some more information, I'm going to watch the video. I've been watching the video that you put on YouTube.
That's good. Nora, do you have a question? You've been very patient. And you've been sitting here very patiently for an hour, and I haven't asked you if you have a question.
I've just been listening and working on my review and my test, my hand in for tomorrow.
Did you have any questions about your hand in for tomorrow?
Um, I am writing a proof for the first question, and I'm not exactly sure if this is what you wanted, but I think this is. It's you gave us a formula, and I'm writing for I equals 1 summation n,
Uh-huh,
I equals n times n plus 1 over 2.
uh-huh.
That's for the formula that you gave us. And then I expanded it. And then I was going to try to show that this formula multiplied by 20 gives us the values for which we are solving for.
That's exactly right. That's exactly right. On quiz number 8, that is exactly right. That when you look at 20 plus 40 plus 60 plus 80, keep on going up to 40,000. You saw it. Yeah, we just pull out the 20 and then we see a sum to which 20. So 20 comes out of 40,000. 2 would be 20,000, 20 would be 2,000. I think it's 2,000 left, right?
Yes. And that brings me right into my next question because I'm trying to write them with summations because they are a summation. So I have I equals 1 summation 2000 for 20I.
Yeah,
That's the
that
sequence.
actually does work. That is actually correct. But I want to leave the 20 on the outside, and I'll tell you why. But you could bring it on the inside.
Well, I had it, well, to be fair, I had Oh no, I had bought it on the inside. Oh my goodness.
But you know, I mean,
Okay.
the point is the constant term will slide in and out, just the same way this 20 can slide in and out of this parentheses. So the bottom line is though the formula that we have something, we have the formula for this. We don't have the formula for this with the 20 on the inside. But again, the 20 on the inside can just slide out to the outside, and then you use the formula. I mean,
Oh,
see what I mean? This really is equal to the sum from I equals 1 to 2000 of 20I. But we don't have a formula for 20I. We have a formula for the sum from I equals 1 to n of I. We don't have a formula for this. But just pull it outside, and then it looks like this.
oh, okay. And on the left hand, oh, well, the right hand side, it becomes 20 times n plus 1 over 2.
Exactly.
Okay.
20 times. Yeah, n is 2000, right?
And then when I go to prove this, then could I say something like for the for this part, n would be n equals 2000?
Exactly. And in fact,
Okay.
proving it would just be showing this looks like this, looks like this, looks like this, where n is 2000.
Okay. All
That's
right.
that's all that the proof requires.
Okay. That's really great. I was working on this while I was listening, and my what I've written looks like what you have there. So I'm really
Oh, that's
happy.
awesome. Oh, how gratifying is that?
I'm struggling with the indexing. Something that confuses me. I understand when I equals 1 or I equals 0. I understand that when we substitute, that's our base value.
Uh-huh.
But I don't quite understand A naught, except it's the first value in the sequence.
Well, it depends upon, the sequence, but yes, it depends upon the sequence. Some sequences have indexing that starts at 0.
But I don't understand the A value. Is that how, because it goes,
It's not a value as much as a term. Um,
oh,
you know, if we say we have a sequence A naught, A1, A2, A3, dot, 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 that's just very generic. We don't know anything about the sequence, we have no idea.
so it's just a variable and an index
What
value?
A sub n is. Yeah, yeah. So when we say, however, when we are told, hey, A naught is 1, and then the next value is 3, and the next value is 9, and the next value is 27, and the next, term is 81, even though it's not written, we're just being basically given enough information to be told the indexing is starting at 0. The very first term, the initial term is 1. Oh, this is A1. This is A2. This is A3. That's really all this information is telling us.
I remember this. We talked about this when we first began induction and sequences.
Uh-huh. So,
Ah,
so A naught simply is given to you as a way to tell you where the indexing is supposed to start for the sequence.
I see.
I mean, it could have been written a different way. It could have been written 1, comma 3, comma 9, comma 27, where the indexing starts at I equals 0. Well, then you would go back and then you wouldn't know what to call this. You might call it B, you might call it C sub 0, you might call it A naught. So not only is it a way to tell you where the indexing starts, it's also a way to tell you the letter that we want to be using for this sequence, as opposed to, maybe, B naught or, B naught, is equal to, I don't know, -1, then 1/2, then -1/4, you know, then positive 1/8, and then negative 1/16. So we're being told that this is a sequence that's being, the terms are called B sub whatever, and this is B naught, right? But, it could be different. We could be given, C1, we could be told, it starts at C1, or we could be told it starts at C sub 0. And, you know, I don't know. I think I gave y'all one, 1 minus 0 over 1, and then 1 minus 1 over 2, then 1 minus 2 over 3, then 1 minus, remember that one?
Yes, I remember this. This is 1 minus, I think you used n minus 1 over n.
Yeah, that's what it was. Uh, I think it was n over n plus 1.
Okay. Oh, right, right. Because it's
Right,
0. That would be
right,
0.
right.
Okay.
And then,
Okay.
right. I think you put n minus 1 over n, and I was like, don't, that would have worked if it started at z at 1. Like, right?
Oh,
In fact, your answer would have worked if we had been told d1 is 1 minus 0 over 1, and then the next term is 1 minus 1. Your answer would have worked for this
ah.
sequence. Yeah, I remember that. I was like, oh, I'm so sorry. And
I
that's why
see.
we have to pay attention, to where the indexing starts.
Right. Okay.
Did that
I'm
answer your
get
question?
Yes, yes, this was really helpful because there's so many little pieces of information that is terrible. But I'm getting
But
it. I'm
wonderful.
it is
It's
wonder.
it's
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 very
ter it's terrifyingly wonderful. I know, I know, I know. But it's so much fun to give an office hour with you because you always ask for the good stuff, You always dig into the details. And that just indicates to me you really should be a math major. You really should be a double major. I really want to recruit you to be at least a double major because you've got the kind of mind where you could be very successful doing a double major. You want to know the details. No, I'm serious. I really think you should consider being a double major.
Well, I'm having a fantastic time in your class.
So
I get
glad.
lost sometimes in some of the math classes. I've never done poorly in a math class, but sometimes these concepts are so foreign and I don't encounter them at all in my day-to-day that to have your office hours is wonderful.
I'm so glad that they're helpful. And it just amazes me how few students partake. But, they are recorded, right? So, that's great, except that when you go to a recording, you've got no guarantee that your question is actually going to get answered. So, I mean, but you get your questions answered. They're really good questions. So I'm very pleased. Do you have any other questions that I can help you with?
Um, no, thank you, Professor.
You
I'm
think you'll be
doing.
okay with those two induction proofs with products?
Oh yes, and when we did the template, that was fantastic.
I'm so glad. Okay, great. Well,
All
have
right,
a good
thank
night.
you. You too. Take care, Professor. Good
You
night.
as well. Good night.